Okay, we'll get started. I'm sure many more will be joining us from the tutorial session that's just finishing up, but welcome to the session on flexible demand. Our first talk will be given by Lukas Ortmann, who's a PhD student in the Automatic Control Lab at ETH Zurich. He obtained his undergraduate and master's degrees in electrical engineering at RWTH Aachen University in 2014 and 2018. During his graduate studies, he was a visiting student in mechanical engineering at the University of California, Berkeley, and conducted research with the Doyle Group at Harvard University. Lukas, can you share your video?
Yes.
Thank you.
Okay, welcome everyone. I put quite some effort into making a nice video for this, so I'm just going to share that with you, but then I'll be available for questions in person. Okay. Hello and welcome to my presentation on experimental validation of feedback optimization in power distribution grids. This is joint work with Adrian Hauswirth, Caduff, Florian, Dörfler, Saverio, Bolognani. Let's start off by analyzing the problem that we actually want to solve. Imagine you have a distribution grid that is a point of common coupling and then a really long distribution line where we have a wind or a solar farm at the end or some kind of active injection that leads to a high overvoltage at the end of this line. At the same point, imagine you have an electric vehicle that is charging, and therefore we have an undervoltage here on the line. Now the question that we're asking ourselves is, how do we control the reactive power capabilities of these three inverters of the electric vehicle, an inverter connected to something else, and the inverter of the wind or solar park, to control these overvoltage back into the desired range, which in our case is the voltage range from 0.95 per unit to 1.05 per unit. And we can define this as a volt-var problem, and we're going to say, okay, let's find the reactive power set points for all the inverters such that all the voltages are going to be inside the desired voltage range, and all the reactive power set points are within the capabilities of the inverters. There are many combinations of reactive power set points that can achieve this. We're only interested in finding the following one. We're trying to find the one that minimizes a certain cost function. And for example, by choosing M, we could share the workload on the different inverters. So we would just say that M is a matrix that is the inverse of the maximum reactive power capabilities, and then every inverter would need to pitch in with the same percentage of its maximum capabilities. Okay, so right now, this overvoltage problem is solved by local feedback controllers. So every converter is only, or every inverter is only measuring its own voltage and is then deciding on its reactive power set point. And for example, here in this figure, we see the Droop control that is defined in the IEEE 1547, which is basically the grid code at the moment. And that says, if we have a voltage that is less than the minimum, then we're supposed to inject as much reactive power as possible. Whereas when we have a voltage that is higher than the maximum voltage, we're supposed to absorb as much reactive power as possible. We could also define this with an integral controller, where on the y-axis now we have the difference in reactive power. So whenever we have a voltage that is too low, our difference to the next step is going to be positive. So we're going to try to inject even more reactive power. Whereas if the voltage is too high, we would try to minimize and then lower our reactive power set points further and further. Unfortunately, if we take another look at the voltage profile that I showed you, the electric vehicle that is connected here will not lower its voltage any further, which would help to reduce the overvoltage at the end of the line here, because it's already below its set point of 1 per unit. And therefore, local control strategies can actually not solve this specific problem. And this was also mathematically proven on the need for communication for voltage regulation of power distribution grids. There is another approach, and that is a feedforward approach. Imagine you can measure everything on the distribution grid, and also you have a really good model of this distribution grid. Then you could use this model and all the information, all the measurements that you have about this, and solve an optimal reactive power flow problem. And then the result of this optimal reactive power flow problem would be the reactive power set points that you should send to the inverters. And if these inverters would then use these reactive power set points, you would have a voltage profile that is satisfying all the constraints. Unfortunately, this requires a lot of load knowledge. So you would need to know all the active and reactive powers in the grid, and you would also need a good model itself. Unfortunately, both is not available in distribution grids. So how do we solve this optimization problem then? Well, we're trying to minimize this cost function. So we would like to use as minimal reactive power as possible, but we also want to make sure that the voltages are within the range that we define, and also the reactive power capabilities of the inverters have to be satisfied. But as I said, we do not have a model of how the voltages depend on Q, and we also don't know anything about W. And here W is the reactive power and the active power that is flowing through the grid. And now the question is, how do we design a feedback controller that steers our grid to the solution of this problem? And the solution to that is feedback optimization, and that how that works, that's what I'm going to explain next. So first, we're going to start with an optimization algorithm. To do that, we're going to define a Lagrangian. So we're going to say, okay, we take the cost function that we have, and now we're going to add a dual multiplier lambda max and a dual multiplier lambda min. And with those, we're going to dualize the voltage constraints. And then we're going to have a dual update on these dual multipliers, and we're going to have a primal update on our reactive power set points. And right now, this actually looks like an offline feed-forward optimization algorithm, but this is going to develop into a feedback controller that steers our system to the optimal solution of this optimization problem only using measurements locally available at the inverters. Okay, let's take a closer look at the dual update. What we do here is a pretty standard approach in optimization. You can find it in any textbook. We're changing the dual multipliers with a gradient ascent. So we take the old dual multiplier, and now we do plus some step size alpha times the steepest ascent in the Lagrangian. And because these are dual multipliers that are associated with inequality constraints, they always have to be positive. And that's why we add this projection operator with the brackets here, where we always project on the positive numbers. Again, this is a very standard approach in optimization. And then if we actually take this derivative, this partial derivative of lambda, of the Lagrangian with respect to lambda, we get the two equations with which we update our lambda min and lambda max. And what we're actually doing here is we're only locally integrating the voltage violation, because what we get here is we get that lambda at the next time step is the old lambda plus this step size alpha times the voltage violation. So for the lambda max, we take a look at the current voltage at this inverter, we subtract the maximum voltage that is allowed, and if this is positive together with this projection operator, then we start integrating this. And this is the lambda update. We also have the primal update, and here we're trying to solve for the argmin in Q of this Lagrangian Lagrangian function, where we plug in the newly calculated dual multipliers. And as in any standard approach to finding a minimum, we just say, okay, let's take a look at where the derivative is 0. And then what we get is the following equation that we set to 0. And here we need to take the partial derivative of the voltage with respect to the reactive power. This is a nonlinear equation, but we're just going to assume that we can approximate this with a constant matrix X. And if we do that, then we can calculate the unconstrained Q like this. Why unconstrained? Because up until now, we ignored this constraint that Q needs to be inside Q. So all the reactive power set points that we calculate are supposed to be inside the capabilities of the inverters. And now to make sure that this constraint holds, we're going to finally calculate our reactive power inputs, set points, as this argmin. This is a quadratic program. It's a quadratic cost function with linear constraints. So it's really easy to solve within sub-seconds, even for thousands or even millions of variables. So this really is not a problem for our algorithm. So now we have our lambda update and our Q update. And with that, we can take a look at our block diagram. In the blue area, we have the controller. The controller consists of this lambda update and the Q update. In the gray box, we have the physics. That is the distribution grid and the inverters. And now what happens is the inverters take a voltage magnitude measurement and send this to the controller. The controller then uses these voltage magnitude measurements to do the lambda update. And with this newly calculated lambda, we're going to do the Q update, as I just showed you on the slide before. Then the controller is going to send these newly calculated reactive power set points to the inverters, and the inverters are going to actuate the grid. Then shortly after, they're going to take a new voltage magnitude measurement, and then they're going to do that over and over again as every normal feedback controller. But in our case, this makes the system converge to the optimal solution of this optimization problem that we defined up front. Okay, let's take a look at the model information that we need to implement this. As I already said, we need this derivative of the voltages with respect to the reactive power set points. And we are assuming that we can approximate this by a constant X. And this models the sensitivity of the voltages with respect to Q. So if you change Q, how much are the voltages going to change? This information is going to be told to us by X. And it can be calculated by using topology and cable data, and it's similar to power transfer distribution factors. Luckily, we can also have a model-free approximation where we just say, okay, all the voltages are affected by a change in the reactive powers at any point in the same way, so everything is just going to be 1. Okay, now let's take a look at the first, at the hardware setup that we have. Luckily, we had the opportunity through the ARIGRID program to have access to the SysLab laboratory in Roskilde in Denmark. So what you can see here is a picture of this laboratory. And what you see is we have 4 different buildings. And in these 4 different buildings, we have bus bars. These bus bars are connected with cables. And you can also connect all kinds of different devices to these bus bars. And what we did is the following. We built the following topology. On the left side, you see the cables and the devices that we used. And on the right side, you see the corresponding topology. So we built this topology that I showed you in the beginning, where we have an electric vehicle, which we built from a static load and a PV inverter. We have a PV inverter here and a battery at the end. We didn't use a solar or a wind park, so we could use the battery and have repeatable experiments because the battery can always do the same thing. Mention that the colors here corresponds to the colors on this side. And what we have here is exactly what we see on the right side. We have 3 different inverters marked by these eyes here. And we're now going to apply the 3 different controllers that I showed you, the local controller, the optimal reactive power flow controller, and our feedback controller to this grid, and we'll see what happens. These are the active and reactive power capabilities. So the battery is working at 10 kilowatts, the static load is working at 15 kilowatts, and the reactive power capabilities of the PV inverters and the battery are also reported here. So let's first take a look at what happens with the optimal reactive power flow approach. What we can see here is 20 minutes of experimental data. And on the right y-axis, we have the reactive power that the PV1, PV2, and battery inject. And on the left side, we see the voltage, that's the blue curve, also measured at the battery PV2 and PV1. So after 3 minutes, we activate our controller. And because of a large active power injection at the end of the feeder, we have this high over voltage at the battery. And remember that the voltage band is 1.05, so we have a voltage over voltage of roughly 0.02 here. So at minute 3, we activate the controller. And what happens is that the optimal reactive power flow problem collects all the measurements from the grid, which is possible in this laboratory, but wouldn't be possible in a real grid. And we also have quite a good model of the grid in this laboratory, which we also do not have in a real grid. Nevertheless, even though we have this very accurate information, the solution of the optimal reactive power flow problem leads to reactive power set points of the battery, PV2 and PV1, that actually do not lead to a voltage at the battery that is within the voltage range. So due to model mismatch, we have a slight over voltage here. And yeah, so we have a steady state error with a voltage violation. Now let's take a look at what happens with the local controller, the Droop controller that I showed you up front. Again, after 3 minutes, we activate our controller. What happens is that the battery sees this over voltage and starts to reduce its reactive power to its minimum value. This lowers the voltage, but it doesn't lower it enough to get it back into the voltage band. PV2 doesn't see an over voltage and therefore is not reacting at all. PV1 actually sees an under voltage that is that severe that it starts injecting reactive power, which then makes the over voltage at the battery even worse. So in this case, the Droop control actually, at the PV1 actually makes the problem worse. And if this would be a real active power injection at the end of a solar park or a wind turbine, and not just in a laboratory, then we would need to curtail this active power so that we would not have this persistent over voltage. And therefore, PV1 would actually lead to more renewable energies being curtailed. That's something that we definitely don't want. So yeah, reactive power of the PVs is not used, and therefore we have this persistent over voltage. Now we're going to take a look at what feedback optimization does. Again, at minute 3, we activate our controller. The battery sees this large over voltage, and within the lambda update, the battery starts integrating this voltage violation, which leads to all 3 inverters to lower their reactive power. And as long as there's an over voltage, we keep integrating this voltage violation in the lambda update, and this leads to the reactive power set points being lower and lower until we finally converge exactly to the threshold of the voltage band. Then if at minute 12, we actually release this active power injection at the battery, so we do not inject any active power anymore, then the voltage drops down and all the reactive powers also go back to 0. And then here at minute 14, we repeated the same thing, and we can see the same behavior, which is we see convergence to the allowed voltage band. And I told you before that we are even able to implement this without any model information. So we can assume that X is just all ones and it still works, because actually here you can see the data for the model-free version. It works really well. So with that, I would like to conclude that all local control strategies can make these under and over voltages worse. Luckily, feedback optimization can solve the problem. It has great potential for power system applications, and it's very robust, as we just saw. Now, finally, I would like to thank my co-authors, Adrian, Ivo, Florian, and Saverio, and also the funding that we received through the Horizon 2020 program of the European Commission, which enabled us to do this research at the Technical University of Denmark through the AeroGrid program. And with that, I would like to thank you for your attention. Okay, thanks everyone. I'm now happy to take any questions.
Are there any questions? You can feel free to type them in the Q&A box. I'm sure that there are some coming. I have a question. So you applied it to a balanced case, is that right? What if you had voltage unbalance?
To be honest, we didn't analyze that at all. We always assumed that we would be working with a balanced case. So I can't really answer the question, to be honest.
Okay.
Given that it is quite robust, as we saw, I guess we wouldn't run into large problems. But yeah, we didn't analyze it.
Okay. And Dan Wilson was asking a question. He
Yes,
says,
there are.
Can you read it? Can you see it directly?
Yes, I'll take care of it. Let's start with Dan. So Dan says, hi, Lucas, thanks for the presentation. Can you comment on how well your controller behaves after large failures? Also, unfortunately, I can't. We didn't test that in Denmark. Then Matt's is asking a question. Does it matter if network is meshed? No, that does not matter. It can either be a long line as we had it, or it could also be a mesh network. It could even be a disconnected network, but then you can also apply to two different controllers for each part. And then Pedros is asking, it seems that the sensitivity of voltage to reactive power injection, the matrix X, is necessary. Don't you need a model to compute X? What is the impact of having an X with arrows? That's a very good question. Yes, if you want to calculate it, then you need some kind of model assumption, and you need some parameters of the cables that are in your grid. But as I said, you can always use an approximation. So if you have a rough idea what the diameters are of these cables, then you can approximate these values that you need to put in the X matrix. And also, as we saw in the measurement data at the very end, so this is actually the case where we said, okay, X is just all ones, so we don't know anything about the real parameters. And as we saw, it does still work.
Any other questions?
Yes, there's one more question from Matt. And Matt is asking, thank you for the nice presentation. Can you tell us a bit more about if you think there is any issues with introducing feedback into distribution grids generally with regards to TSO and DSOs? This will presumably make transmission system operation much harder if distribution grids become very voltage sensitive. So first of all, I actually think that this could be an advantage. So if you're able to control your distribution grid to behave in a certain way, then you can actually start using it to provide auxiliary services to the transmission grid. So for example, if the transmission grid has some voltage problems or some overcurrent problems, they could ask a certain part of the distribution grid to provide certain reactive power flows, and with them you could maybe solve your overvoltage or overcurrent problems in the transmission grid. So I guess it's going to make the whole thing more challenging, but actually in a positive way, because with all the intelligence and all the actuation that we bring in there, we can probably do some really smart things.
Great, thank you very much for your excellent presentation. I think we'll move on to the next one.
Okay.
So
thank you all for listening.
Thank you. Chiddish, can you share your screen now?